what is stress concentration? Why does it happen? What happens? So it's clearly something to do with stress being concentrated. It really means in this case, the stress is higher than what you normally would expect it to be. And the reason why the stresses are higher is because when you make a design for any mechanical element, you don't necessarily end up with a uniform design having a regular shape like a circle or a cuboid. You have things like grooves, corners, shoulders, edges. All these things introduces stresses because of the change in geometry, and that's the focus of this part. So regular geometry would be like cylinders, cubes. You have we'll have uniform stresses. The moment you have irregular geometry, and they would become due to corners, shoulders. You would have a higher stress, so higher than normal stress when the geometry changes. Okay, so what are some examples? Okay, so if you have a bolt or a screw, and then you have these threads, those threads cause concentration of stress. The change in geometry here will cause stress. So screws, bolts, nuts. Okay, so the change in geometry is here and here. Then you have another way in which you get these things is when you have shafts, you have grooves in them. So this are keyways so that you can keep the shaft and the when you connect to shafts, you have this groove so that you can put things together, place them together. And so that introduces stress. So here is a shaft, and what they do is they put a key seat like so. And then the key basically would then go onto another shaft, which is hollow. I'm trying. So this is our key. This is the shaft with a keyway, or let's just call it keyway. Okay, so that key can go in the keyway, and then it will, the way you mate it with another shaft is that there is a corresponding groove. This is for the key. So when you put things together this fashion, they actually stay together without you having to affix them with additional elements. So transmission shaft with keys and keyways will have stresses showing up on the shaft. So you just can't have just a shaft. You need something else to hold them together. Other things, as I said, are shoulders, grooves, notches, etc. all lead to change in geometry, hence lead to stress concentration. Okay, so the way we quantify the stress concentration is uh, there's a factor for stress concentration called, well, stress concentration factor, and I'll just define it. So stress concentration factor so KT is sigma max divided by sigma O, and I'll tell you what the sigma max and sigma O are. Similarly, for shear stress, there'll be tau max divided by tau zero. So what are sigma max and tau max? So sigma max and tau max are the maximum normal and shear stress or stresses at the discontinuity. And then sigma 0 and tau 0 are the nominal stress, or the nominal normal and shear shear stresses in the absence of the discontinuity. So assume that that groove was not there, or that keyway was not there. What would be the stress? That would be the normal stress, which we have tools to compute. So we have tools to compute sigma 0, tau 0, and they come from some of the calculations we've done in the class. You could also use finite element analysis. If you don't know, it's a package to find stresses. It's one of the many things you can do. But then the problem is you cannot find sigma max, tau max that easily. So what people do is they use experimental methods to find tau max and sigma max, and then they define these tables where you can find this KT and KTS, which are basically now properties of the geometry and not of the material. And from those tables, you can figure out what the maximum stress is. Okay, so we'll come to that, what I said just in just a bit, but KT and KTS are functions of geometry, okay, not of material. Okay, and they are found experimentally Okay, and then the techniques to finding them experimentally, if you if you're curious, it's called photoelasticity. Other one is strain gauges. And then there's this one, I don't know, brittle coating. This from the book. I have no idea what this is. Coating methods. And grid methods. I've not heard of these two, but then I've heard of photoelasticity and strain gauges. Photoelasticity is purely a visual kind of method to figure out stresses. It's non-contact. And the strain gauges is really you need to paste these elements to the material to measure the strain, and from which you can get the stress, knowing the elastic modulus of the strain gauge. Now, FEM, finite element methods, which some of you might be taking a course, are not so good at figuring out the maximum stresses, because stresses usually require the elements to be of infinitesimally small size, and then that just breaks down into FEM, because FEM relies on having finite elements. It's not, cannot be too small. Okay. So experimental is the way to go. Okay, so what I was saying was, once you set up these photoelasticity and strain gauge experiments, you can find KT and KTS. And those are properties of the geometry. And so here is an example of what you will see in terms of a table. It's actually a picture here, but you could also put this in a table. So I'm going to pick this from the book. Okay, so here is an example of stress concentration on the y-axis for this particular piece of block. So the block, if there was no hole, which you can see in the middle, then the stress would be uniform. It would be sigma divided by the width W times the thickness, which is actually in the plane. It's not shown here. So that will be the normal stress. However, if you introduce a hole and the hole diameter is D, then it turns out that depending on the ratio of the diameter of the hole and width of the plate, the stress concentration will keep changing. So as the ratio increases, you can see that the stress factor KT keeps going down, which means that the maximum stress also moves down. So the way they found this is through one of those experimental methods, right? So you got KT. So given the dimensions, I can find, so given a D and W, I can find what KT is. And then I know what sigma is. Sigma 0 is because, I apply the load. So I can find sigma, what sigma is. I can find sigma max using that formula. And I'll do a problem based on that. Here's another example of how to use some of this for another geometry. This are okay. So this is a different example where there's a corner, circular corner, and so here it's a bit more complicated. Here you need to have two ratios. One is capital D divided by small d, which is the area, sorry, the length of the larger section to the smaller section, as you can see. And so you need to first find that. Once you find that, and let's say it's 1.1, then you are going to be on this line for KT. And then you find the ratio of the fillet, the R, divided by D, small d, and that will give you exactly where you want to place the dot, which gives you the KT, and then you can use that KT to find the cost. Just, yeah. This, say that again. If R was a 90-degree angle, would be 0 R divided by small. If R was 90 degrees. It was like an edge. Oh, so then there'll be a different table. I think the book has like a series of tables. I can find it for you. Let me see if there is. I think if you have a corner, it's a different stress factor. It must be much higher than this, but let me quickly check if the book has a table for that. Oh, where is that? Okay. Okay, so I'm checking A15 in the book, and there is no such example. So the question was, what if this was a corner, right? Uh, I guess you can just use this formula. It's probably be higher, but you normally avoid corners because they just lead to more stresses than uh, curves. But there should be a formula somewhere. Otherwise, you can use this table as a conservative estimate of the stress in that case. So the table is A15 in the book. See table A15. Okay, so let's see how to apply some of the things on stress concentration. I think that's kind of important. Your designs will invariably have discontinuities in geometry. It won't be like a pure shaft. So that's the question. What I had it here. Yeah, for some reason it got deleted. Okay, let's pull out the question. Oh, there it is. Okay, so this is a taken straight from the book, in the textbook. So a 2 millimeter thick, which means that this dimension is in the plane of the paper. The thickness is 2 mm. You don't see it in this 2D view. Is loaded actually with a constant force of 10 kilonewtons as shown. The bar material has been heat treated and quenched to raise its strength, but as a consequence, it has lost most of its ductility. It is desired to drill a hole through the center of the 40 mm face. This is the 40 mm face, that's the hole. To allow the cable to pass through it, a 4 mm hole is sufficient for the cable to fit, but an 8 mm drill is readily available. Will a crack be more likely to initiate at the larger hole, the smaller hole, or the fillet? Okay, so there are two options here. You can have a hole which is 4 mm. You could have a hole which is 8 mm. And then both of those radiuses will have different stresses. So that would be the stress here. So that AA. The other place where things might have a high stress is when there's a change in geometry, which is here, right? So B. So what we're trying to do is we are not given what the maximum stress carrying capability of this plate is, right? So that would be typically a criteria to compute where it will fail, but we just want to find which of those three. There are three cases because there are two kinds of holes you can make. Those three cases, we need to figure out which of those cases will have the maximum stress. A hole of 4 mm at AA prime, a hole of 8 mm at AA prime, or the fillet, which is shown at BB. So there are 3 scenarios. What's going on? Okay. 1, AA R equals 4 mm. 2 at B at AA prime. R equals 8 mm. Or third one is BB prime. So we need to find the stresses. The 3 places where we will compute sigma max. Okay, so we'll solve each cases one by one and then find the maximum, that's all. Okay, so let's do it one at a time. First, let's do section A for the 4 mm hole. It's what's that? Are you hitting something? No, I don't know. It's the same thing. It should. I don't know why it's flashing on the big screen. This looks fine. Okay, that moved. That's fine. Maybe I'm moving this. Okay, that's all clear now. Hopefully it won't flash again. Okay, so what we are interested first case is there is the hole and it is 4 mm. So okay, so it's my bad. It's not the radius, it's the diameter which is 4 mm. This is not, this shouldn't be, this should be D, right? Okay, so let's say that the diameter is 4 mm. Then the stress, now I just really removed the fillet out of it because really what happens is the stress or the force is transmitted, and so the same force will appear across this section A. I drew a different section which is further ahead, but I just need the stress where there was no hole. So I need to find the effect of this P in inducing a stress first. So this force, I think it's called F, equals 10 kilonewtons. And then this width is W equals 40. And this diameter is 4. Okay, first step is, okay, so we are trying to find sigma max. Okay, and the way we'll do it is, we know the definition of KT, which is sigma max divided by sigma 0, right? And so if we have to find sigma max, we need to find sigma 0 and KT. So we can get sigma 0 is it's the stress when there is no hole. And when there's no hole, the stress is simply the force divided by the cross-sectional area. So the force is 10 times 10 raised to 3 divided by the cross-sectional area when there's no hole at all. So it will be width times the thickness, and we're given that the width is 40 mm, so 0.04. Okay, hold on. That's not right. So since we are cutting it here, which I should have done it in the first place, This is probably the right way to do it. So if we're cutting it here, the stress is borne by this part and this part. And so it's going to be the width minus the diameter. So it should be width minus diameter times the thickness, because it's the section A, my bad. And so W is 40, thickness, the diameter is 4, and I need to divide it all by 1,000 to convert to meters, and then thickness is 2 mm, so 2 divided by 1,000. And so when you do this math, it comes out to be 139 MPa. Okay, so we got sigma 0. Now we need to find KT, and KT is a function of only the geometry. So let me pull that figure from the book for this section. So insert picture, put in this one. Completely messed it up now. Okay, so I need to find KT now. So what I'll do is I'll find D divided by W. So D is 4, W is 40, and so I have 1 divided by 10, which is 0.1. So I just need to read off the KT for 0.1. So 0.1 is here, so KT is right there. That's the KT. I need to get KT is it looks like it's less than 2.7, but I just use 2.7. So let's just stick with 2.7. Okay, as long as you have it in the ballpark, it's fine. So 2.7. So now we have KT is sigma max divided by sigma 0. And so we can say that sigma max is KT times sigma 0, which comes out to be 2.7 times sigma 0, which is 139. And so yeah, sigma max is 380 MPa. So you can see that the stress is actually almost 3 times the nominal stress. That's the effect of stress concentration. KT is a non-dimensional number. It doesn't have a dimension because it's a ratio of stress to stress.
So 50 megapascal.
I get it.
I'm just wondering what's happening with the units. Because sigma max has is in megapascals and
Sigma 0 is megapascals.
Oh, sigma 0, sorry.
So it gets, so it just is the units of sigma 0. Okay, so the next step is to find the stress for case 2. Is to do the same calculation for the 80 mm hole. Okay, which I will, 8 mm hole, which I will skip. I will actually write this down later on since I'm running out of time. But the calculation is going to be exactly same as the one I did for this one. the sigma 0 will change because it has the width and the diameter in it. The KT will change, and then your sigma max will also change. So I'll fill this up, but you should try to do it yourself. Okay, let's go to the last one, which is the fillet. So last one is the fillet. Okay, so here this R is 1 mm. This is 34. This is 40, my bad, 40. And this is 34. So here, the nominal stress is force divided by cross-sectional area. The force is 10 times 10 raised to 3. And the cross-sectional area is going to be, since the force is acting here, it's going to be this area. So 34 divided by 1,000 times the thickness, which is 2 divided by 1,000. So that comes out to be 147 MPa. Now I need to find KT. And for KT, I'm going to pull out, let's just do it from that figure. I'll fill this, I'll put that figure here later since I'm running out of time. Let's just go to the other figure I pulled. Okay, so here what I need is the D divided by D. So D is 40, small d is 34. That's D, so D divided by D is 40 divided by 34, and that comes out to be 1.18. And then I need R, small r divided by D. So small r is 1, small d is 34. So that's 0.026. So 1.18, we have 1.10, 1.5, 1.18 is probably somewhere in the middle, slightly closer towards this 1.10 line. And then I need to find 0.026, which is probably somewhere here. You just assume it to be here. And I mean, it's okay to just assume that it's there. It's actually slightly above that, right? So that point is KT equals 2.5. It's okay if you make this approximation. You don't have to be exactly right. Just give me a 30 seconds and I'll be done. So I got KT equals 2.5. I go back to the problem. I put in the value 2.5. And then I need to find sigma max, which is KT times sigma 0. So it's 2.5 times 147. And that comes out to be 368 MPa.